This edition of SpaceTime is brought to you by Audible.com. Get a free audiobook download and a 30-day free trial at www.audibletrial.com/spacetime. Over 180,000 titles to choose from for your iPhone, Android, Kindle, or your MP3 player. That's audibletrial.com/spacetime for your free audiobook. This is SpaceTime, Series 20, Episode 6, for broadcast on the 20th of January, 2017. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, monstrous black holes discovered hiding in our cosmic backyard. More evidence for cycles of wet and dry periods found on Mars. And cosmic dust on your roof. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Like monsters hiding under the bed, two enormous black holes have been discovered, lurking behind clouds of gas and dust in galaxies close to our own galaxy, the Milky Way. The giant gravity wells, known as supermassive black holes, were detected by NASA's NuSTAR spacecraft, the Nuclear Spectroscopic Telescope Array. The two monsters were discovered by the high-energy X-ray emissions they were generating as they fed on anything that ventured too close. Although relatively nearby, the black holes weren't previously noticed because they were cloaked behind gas and dust clouds near the centres of their respective galaxies, allowing them to hide in plain sight from the gaze of most telescopes. Both of these black holes are the central engines of what astronomers refer to as active galactic nuclei, or AGNs. They're a class of extremely bright objects that include quasars and blazars, powerful energy beams often visible right across the universe. Depending on exactly how these galactic nuclei are oriented and what sort of material surrounds them, they can appear very different when examined with different types of telescopes. Active galactic nuclei are so bright because the particles in the regions around the black holes get very hot, emitting radiation across the entire electromagnetic spectrum, from very low-energy radio waves right through to high-energy X-rays and even into gamma rays. However, the most active galactic nuclei are believed to be surrounded by a donut-shaped region of thick gas and dust, which obscures the central regions from certain lines of sight. Both the AGNs that NuSTAR's recently discovered appear to be oriented in such a way that astronomers are viewing them almost edge-on. Now that means instead of seeing the bright central regions, our telescopes are primarily seeing the reflected X-rays from the donut-shaped obscuring material. The study's lead author, Peter Borman from the University of Southampton, says just as you can't see the sun on a cloudy day, astronomers couldn't directly see just how bright these AGN really were because of all the gas and dust surrounding the central supermassive black hole. Borman led the study of the active galaxy known as IC 3639, which is 170 million light-years away, relatively close in cosmic terms. Researchers analysed the NuSTAR data from this object and then compared that with previous observations from NASA's Chandra X-ray Observatory and the Japanese-led Suzuka satellite. The findings from NuSTAR, which are far more sensitive to high-energy X-rays than the other observatories, confirm the nature of IC 3639 as an active galactic nucleus. NuSTAR also provided the first precise measurements of exactly how much material was obscuring the supermassive black hole at the centre of IC 3639, thereby allowing researchers to determine how luminous the hidden monster really is. Even more surprising was the other supermassive black hole detected by the team. It was discovered in the heart of a large spiral galaxy NGC 1448, which is located just 38 million light-years away. The X-ray emissions from NGC 1448 as seen by NuSTAR and Chandra suggest for the first time that, as with IC 3639, there must be a thick layer of gas and dust hiding the active black hole in this galaxy from our line of sight. Researchers also found that NGC 1448 has a large population of young stars, only around 5 million years old. And that suggests that the galaxy is producing new stars at the same time as its central supermassive black hole is feeding on gas and dust. The researchers then used the European Southern Observatory's New Technology telescope to image NGC 1448 at optical wavelengths, allowing them to identify exactly where in the galaxy the supermassive black hole should be. Although all galaxies are thought to contain a supermassive black hole at their centre, the exact location of the object can often be hard to pinpoint because the centres of galaxies are so crowded with stars. But large optical and radio telescopes can help to detect the light from around the black hole so that astronomers can find their location and piece together the story of their growth. NuSTAR project scientist Daniel Stern from NASA's Jet Propulsion Laboratory in Pasadena, California, says it was exciting to use the power of NuSTAR to get important and unique information about these beasts, especially the fact that they're in our cosmic neighbourhood where they can be studied in such detail. NuSTAR is a space-based X-ray telescope launched in 2012 on an Orbital Sciences Pegasus rocket from the underbelly of a Lockheed L-1011 TriStar airliner into a 620-kilometre high orbit. The 350-kilogram spacecraft is equipped with 2 telescope-focusing optics on a 10.2-metre deployable boom that extends out from the satellite's main body, allowing astronomers to search for X-ray sources throughout the universe. You're listening to SpaceTime. I'm Stuart Gary. NASA's Mars Curiosity rover has discovered what look like mud cracks on the surface of the red planet. If the interpretation holds up, these will be the first mud cracks, technically known as desiccation cracks, confirmed by the Curiosity mission. They would be evidence that the ancient era when these sediments were deposited included some drying after wetter conditions. Curiosity science team leader Nathan Stein from Caltech in Pasadena, California, says the 6-wheeled car-sized robotic rover has spent several weeks examining slabs of rock cross-hatched with shallow ridges that likely originated as cracks in drying mud. The site, which has aptly been named Old Soka, is located on a lower section of Mount Sharp, the central peak inside Gale Crater. Curiosity's already found evidence of ancient lakes in older lower-lying rock layers and also in younger mudstone above the location of the Old Soka site. Stein says that even from a distance, scientists could see a pattern of 4- and 5-sided polygons that don't look like the sort of fractures previously seen by Curiosity. Rather, they look more like something you'd see beside the road where muddy ground has dried and cracked. However, in this case, the cracked layers formed more than 3 billion years ago. They were subsequently buried by other layers of sediment, all becoming stratified rock. Later, wind erosion stripped away the overlying layers. Material that eventually filled the cracks resisted erosion better than the mudstone around it, so the pattern from the cracking now appears as raised ridges. The team used Curiosity to examine the crack-filling material. Cracks that form on the surface, such as drying mud, generally fill with wind-blown dust and sand. A different type of cracking, with plentiful examples found by Curiosity, occurs after sediments have hardened into rock. Pressure from the accumulation of overlying sediments can cause underground fractures in the rock. These fractures are generally filled by minerals delivered by groundwater circulating through the cracks, such as bright veins of calcium sulfate. Both types of crack-filling material have been found at Old Soka. Scientists think this could indicate multiple generations of fracturing. Mud cracks first, with sediment accumulating in them, then a later episode of underground fracturing and vein forming. Now, if it's suspected these are indeed mud cracks, they fit well within the context of what scientists have been seeing in this section of Mount Sharp, which Curiosity's been climbing over the past few months. The ancient lakes in the region varied in depth and extent over time, sometimes disappearing altogether. So, what does it all mean? Well, it seems the research team is seeing more and more evidence of dry intervals between what had mostly been a record of long-lived lakes. Beside the cracks that are most likely due to drying, other types of evidence observed in the area include sandstone layers interspersed with mudstone layers and the presence of a layering pattern known as cross-bedding. This pattern can form where water's been flowing more vigorously near the shore of a lake or from wind-blown sediments during dry periods. Scientists are continuing to analyse the data acquired at the site and are now looking for similar formations. They want to check for clues not evident at Old Soka, such as the cross-sectional shape of the cracks. As for Curiosity, it's now moved on from the site, and it's continuing to climb uphill towards a future rock drilling location. Meanwhile, Curiosity engineers at JPL are still determining the best way to resume the use of the rover's drill. It's been experiencing intermittent problems over the past month with the mechanism used to move the drill up and down during operations. Curiosity landed in Gale Crater back in 2012. It then began a lengthy trek across the crater floor to reach the base of Mount Sharp in 2014. During the journey, it found evidence on the surrounding Martian plains of ancient lakes which offered conditions that would have been favourable for microbes, if Mars had ever hosted life, that is. The rock layers forming the base of Mount Sharp originally accumulated as sediments within the ancient lakes billions of years ago. On Mount Sharp, Curiosity's been investigating exactly how and when those habitable ancient conditions which the mission detected earlier evolved into the drier, less favourable conditions for life evident today. Mount Sharp was chosen as the target for the Curiosity rover because it's considered to be a sort of geological layer cake of different mineral types all laid down at different times in the red planet's history. I'm Stuart Gary. You're listening to SpaceTime. Okay, let's take a break from the show and talk about one of our sponsors. Audible's offering a free audiobook download with a 30-day trial to give you an opportunity to check out their service. Audible have over 180,000 different titles to choose from, such as Contact by Carl Sagan or A Brief History in Time by Stephen Hawking. Others include the unabridged version of The Hobbit by R.R. Tolkien, Divergent by Veronica Roth, and Born to Run by Bruce Springsteen. So many great books no matter what your taste. Over 180,000 titles to choose from. To download your free audiobook today, go to audibletrial.com/spacetime. That's audibletrial.com/spacetime for your free audiobook. Or you can click on the link at spacetimewithstuartgary.com. And now, back to our show. Scientists have found traces of cosmic dust on rooftops across Europe. The space dust particles, which technically are micrometeorites, were found on the tops of buildings in Paris, Berlin and Oslo. Space is a dusty place, and scientists have known since the 1940s that cosmic dust is continually raining down through our atmosphere. However, up until now, the idea of separating the dust from space from the everyday terrestrial dust, dirt and pollution that normally floats in the air and eventually settles on rooftops and in the rainwater gutters has been impossible. What's changed now is that scientists have for the first time been able to isolate 500 space dust particles from some 300 kilograms of roof dust using magnets to carefully sift through minerals and then examine the composition of each of those particles. The grains are known as silicate-dominated S-type cosmic spherules. The tiny particles are only around 0.01 to 0.03 millimeters in diameter, and they all show signs of melting. That's caused by the heat of atmospheric entry at speeds of around 12 kilometers per second. The findings reported in the journal Geology indicate the newly discovered micrometeorites all contain subtle crystal variations in their structure which resemble other samples dating back from medieval times. Now that's in contrast to far older micrometeorites found in Antarctic ice core samples, which are tens of millions of years old and feature a very different type of crystal composition. Scientists think that could indicate different origins for the samples, caused by minor changes in planetary orbits due to gravitational perturbations. To find out more, Space Nuts Andrew Dunkley is speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
Now, when people think of cosmic dust, they probably think of giant dust clouds spanning many light years in space that create planets and stars in some cases, all that kind of jazz. But no, we're talking cosmic dust that's been found on the roofs of buildings in Europe, which is probably the last place you'd look for cosmic dust, I imagine.
That's exactly right, because until now people have looked principally in Antarctica or the deep oceans of the world to find these particles. We know that the Earth's environment is dusty. The evidence for that is clearly that we see meteors, shooting stars in the sky quite regularly. Meteors are just particles of dust that hit the Earth's atmosphere and vaporize. They burn up completely. We estimate that something like 50 to 100 tons of dusty debris falls on the Earth every day.
Wow.
So it's actually quite a lot. Quite a lot of stuff comes down. And as I said, most of it burns up in the atmosphere, but some of it doesn't. The larger objects that make it through the atmosphere, we call them meteorites. But there is also a population of small dust particles which basically they hit the atmosphere at high speeds and they lose a lot of their mass by vaporization, but they make it down to the surface. And in fact, probably quite a lot of dust on the Earth has come from space. But the problem is, how do you find it? So, as I mentioned, one way is to look at pristine environments, to sort of take samples of ice from Antarctica, because then you've got stuff that just lands and settles on the surface of the ice.
Yep.
And you can get a good idea of what the cosmic dust that is there. And actually, deep oceans is another source. I do remember these things used to be called Brownlee particles. I think they were discovered by a Dr. Brownlee in the 1940s. Nowadays, they're just called cosmic dust particles. So what has happened with this experiment is that scientists from Imperial College in London and elsewhere have collected almost a third of a ton of dust from the gutters of roofs in Paris, Oslo and Berlin, 3 European cities.
How much?
And then nearly a third of a ton, 300 kilograms.
Of just ordinary dust, general dust?
Yeah, just dust from, that's right.
Okay.
So then what you do is you pass this stuff through a magnetic field. And because the cosmic dust particles often have a high ion content, that tends to separate them out. So you then get an idea of the ones that are magnetic, and then you can use a microscope to sort out which ones have been modified by their passage through the atmosphere. These things are about a third of a millimeter in diameter. And that's what's been done. And out of that third of a ton of dust, they have identified 500 particles of cosmic dust.
Now, Fred, why did they think to look on rooftops in major cities?
I think what's happened is that the technology that allows you to filter through this stuff very rapidly using magnetic fields, that has now got to the state where you don't have to go to a pristine environment to try and find cosmic dust. You can grab dust wholesale from rooftops or wherever and pass it through these sifting systems to try and identify what's cosmic. And that's where the improvement has taken place.
So would this suggest that just about everywhere would possibly have cosmic dust on our roofs and gutters?
Exactly. Even on your house in Dubbo.
Yeah, well, it's got plenty up there, I can tell you.
Yeah. Get up there with a magnet. You never know what you might find.
True.
But don't fall off. No. So that 500 particles is enough to kind of do a bit of an analysis and, see what story these are telling. And first of all, the estimate from the sizes is that these things melted as they entered the atmosphere at speeds of around 12 kilometers per second, which is typical of re-entering objects. Actually, it's often a bit quicker than that, but 12 kilometers per second is kind of normal velocity for things falling down to Earth. They have structure within them that looks like it's got a slightly different appearance from some of the earlier dust particles that have been found in Antarctica. And one of the suggestions is that the Antarctic dust comes from ice samples, and what you're looking at is stuff that's accumulated in the ice over millions of years, maybe not much more than 1 million years, but of that sort of order. Whereas clearly what you find on a rooftop has only come down since the roof has been there.
Yes,
so it's
exactly.
much more recent.
Yeah.
So the difference between these, the fact that there is a structural difference between these two groups of dust particles, the old ones and the new ones, if you can put it that way, suggests that something has changed. And the researchers at Imperial College are suggesting that this is due to the way the orbits of the planets have changed, that what you've got is sort of a different gravitational arena, if you like, within which these clouds of dust have moved. And that might then impact on how fast they hit the atmosphere. And that means that you've got these differences in structure. There's clearly much to learn about this, Andrew. It's a study it's in its infancy, but it might mean that these dust particles, which, by the way, are as old as the solar system, they're 4.5 billion years old, they may carry within them some sort of record of the way the solar system has evolved. And that makes them very, very valuable to scientists.
Yes, indeed. And my roof's only 3 years old, so I've got really brand new cosmic dust. But, just to think that all of that is just about everywhere is quite astounding because, who would have thought that just living in your house, you're catching material from outer space? It doesn't cross your mind.
Exactly. That's right. Actually, it's a Norwegian amateur scientist who first suggested the idea.
That's Dr. Fred Watson from the Australian Astronomical Observatory. He was speaking with Andrew Dunkley on our sister program, Space Nuts. And I'm Stuart Gary, and this is SpaceTime. SpaceX has returned to flight status with the successful launch of a Falcon 9 rocket from the Vandenberg Air Force Base in California, carrying 10 new Iridium telecommunications satellites into orbit. The flight was a double success for the Hawthorne, California-based company, with the launch vehicle's first stage successfully returning to Earth and landing on a floating platform in the North Pacific Ocean. It's the 7th time a Falcon 9 has successfully returned to Earth for refurbishment and reuse on future missions.
LD, verify go for launch. VC, verify Falcon 9 is in startup.
The vehicle is in startup. Stage 1 present in flight.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff of Falcon 9. AVIRC and GNC proceed to procedure 3.170 for post-launch flight operation. GC, move to section post-launch pad operations to secure the pad on net A. Moving to post-launch pad operations.
Falcon 9 performance is nominal as we head downrange over the Pacific Ocean, flying south from the launch site at Vandenberg Air Force Base in California. We're passing through the region of maximum dynamic pressure right now. This is where the high pressure of the atmosphere combines with the speed of the rocket to provide the greatest stresses on the Falcon 9 vehicle. We throttle the engines down as we pass through this phase, then throttle them back up as we proceed on into orbit. The major activity coming up will be main engine cutoff at T+2 minutes and 25 seconds. We'll listen for that, followed shortly after by stage separation and then ignition of the second stage engine. Let's listen in as the Falcon 9 continues to head downrange, preparing for shutdown of the first stage and stage separation
10,
and ignition of the second stage.
8, 7.
We've had successful shutdown separation of the Falcon 9 first stage. The second stage engine is lit. We're coming up on 3 minutes as we head into low Earth orbit. Everything looking good.
So as you just heard from John Innsbrucker, it sounds like the Falcon 9 first stage has successfully separated from the second stage, and the second stage engine has successfully ignited. It means we're on our way to orbit.
One of the cool things that's about to happen is we are going to begin the recovery operations, or rather the first stage flyback operations.
That's going to consist of that flip maneuver where the rocket is moving in one direction and it will actually flip itself over. Then it will light the engines on the back end, and that will begin a boost back burn to bring the first stage back towards the drone ship. Next up, I think we have a re-entry burn, and that'll slow down the rocket from about 2 kilometers per second down to 1 kilometer per second. It's still really fast, but any sort of decrease of energy that you can get in moving that direction is going to be better for decreasing the aerodynamic stresses on the vehicle.
And the last and final burn, coming up just a little bit later, is going to be the landing burn. That's when the first stage, right as it gets close to the deck of Just Read the Instructions, slows itself down, opens up its landing legs, and prepares for a soft touchdown on the deck of the autonomous spaceport drone ship.
And just to remind you guys, this is an experimental secondary part of this mission today, but obviously something we all get really, really excited about here. But the primary mission is launching these satellites, right?
Mm-hmm. I believe we've already separated the fairing, and that's to get rid of the excess weight, the excess mass rather, so that for the same force you can accelerate faster. I'd say, again, moving at 8 kilometers per second is the final goal to be circling the Earth, which is, again, 10 times the speed of a rifle bullet. As much help as you can get to minimize the amount of mass that you need to accelerate to that speed is better.
Yeah, the fairing is kind of like it's just a big windshield for the satellite. Satellites really aren't built to withstand intense aerodynamic forces. They're meant to operate inside the vacuum of space. So what we do is we lose that fairing as soon as we get out of the atmosphere, and that's where we are right now.
Yes, and so, look at that. You can see that the first stage skid fins are deployed. Now, those skid fins are powered by nitrogen thrusters, and they're used to actually steer and guide the rocket back down to Earth.
They're useful both at high speeds when you're moving at very supersonic and again when you're starting to move slower, but not when you're going through the transition of the speed of sound. They become less helpful.
We're at T plus 5.5 minutes into the flight. Second stage continuing to head downrange as we go into what will be the first of two orbits, the low Earth orbit, followed by a coast phase, then a reignition of the second stage engine later on this morning to get the 10 Iridium satellites into their final orbit. We're coming up on the next first stage event, which will be in about 17 seconds, which is beginning of the entry burn, which will then be followed shortly after that by the landing burn. And we're coming up on the engines. We have boost back burn. You can hear the applause in the background from the SpaceX team gathered around the Mission Control Center as we're watching the 3 Merlin engines on the first stage light, and we have got shutdown for the boost back burn. So currently we're coming up on T plus 7 minutes. Second stage continues to head into orbit. First stage is coming back to the drone ship. Let's go down to the floor for the landing burn and the entry into orbit of the second stage.
The re-entry burn for the first stage has just completed and looks successful.
Little puffs of what look like smoke coming out from between the grid fins every once in a while. Those are part of the attitude control system. I think this is the landing burn.
Looks like the landing burn has just started, so we should be coming right down on the deck of Just Read the Instructions.
This is a single engine landing burn, so it's a slower decrease in speed.
Second stage carrying 10 Iridium satellites has gone into the parking orbit. You also heard the cheering. We actually saw the first stage come all the way back to the drone ship. Didn't have the video dropouts like we've had in the past, so it was an amazing ride with the first stage. And the answer is it looks like we've got a good parking orbit for the Falcon 9 second stage. We're into a coast period now that's going to last up until about T plus 52.5 minutes before we relight the second stage engine. So currently, it's been a great morning so far.
The 70-metre tall launch vehicle has been grounded since September the 1st. That's when a Falcon 9 exploded during fueling on the launch pad at the Cape Canaveral Air Force Base in Florida during a planned static fire test. The blast destroyed the $62 million Falcon 9 and its $200 million Israeli telecommunications payload satellite, which is being launched for Facebook. Accident investigators eventually traced the cause of the launch pad explosion to a faulty composite structure used in a liquid helium reservoir mounted inside the upper stage liquid oxygen tank. The helium's used to pressurize the liquid oxygen during flight. SpaceX has now instigated new fueling protocols until the helium tanks can be redesigned. This week's launch is the first of 27 flights planned by SpaceX for this year, needed to clear up the backlog caused by the September failure. It's also the first of 7 flights contracted to Iridium to launch their new satellite constellation under a $470 million contract. As well as dozens of commercial satellite launches, SpaceX is also contracted by NASA to carry both crews and supplies to the International Space Station using their Dragon and Dragon V2 capsules. The company also has plans to fly a Dragon spacecraft to Mars next year and to undertake the maiden flight of its new Falcon Heavy launch vehicle. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.